Swayam Prabha. Digital India. Educated India.
Good morning. I am delighted to introduce Dr. Manu Jaiswal, a distinguished faculty member at IIT Madras, who has extensive experience in a variety of fields ranging from classical and quantum physics to experimental and condensed matter physics. Dr. Jaiswal obtained his bachelor's degree from St. Stephen's College in Delhi and then completed his master's and PhD at IISc Bangalore. We are eagerly looking forward to his lecture and are grateful for the opportunity to learn from his expertise. Welcome, sir.
Good morning, all of you. Thank you for the kind introduction. I hope this is reviving some memories from COVID time. At that time, you must have been in class 7. So, welcome to this talk on physics of percolation. And I hope you are able to recognize, I was overhearing what these characters are. Even I can name some of them. This is Shinzu, Ninja, Kenichi, Shishimaru. What's the name of this cat? Kyo. Okay. So in this talk, we'll learn about role of geometry in physics, especially role of dimensionality, how that affects physical processes. Then lattice and absence of lattice, which is disorder, what is the kind of role that it plays in physics. And the concept of universality is not that we are dealing with one topic in physics, but actually this touches upon so many topics in diverse fields like chemistry, maths, or even other technology, economics. All of this can be touched upon with the physics of percolation. Since we talked about COVID just a while ago, so I think this will be a good starting point. This is familiar to all, trying to put this COVID mask. Even nowadays, I continue to use it because there is so much dust around. But in the beginning, there was a lot of problem. We would buy a mask, it will be written, it's very good for protecting you from the virus. But sometimes you will feel suffocated. You won't be able to breathe. And if we examine the structure of this COVID of certain size, a middle layer which has denser fibers, and then an outer layer which also has a coarse network of fibers. The reason I am showing this, these dense network of fibers are what is actually filtering the particles. So this could have been some collection of bioparticles which has the virus and that should not reach your nose. So the mask is able to filter this. The physics of percolation or the maths of percolation actually started with the work of Hammersley and Broadbent in 1957 when they were looking for gas masks for coal miners. Coal miners don't have to be protected from virus, but there is a lot of coal dust which if it goes into the lungs, it can't be pulled out. It's there permanently. And these people used to suffer from respiratory disorders. They worked on the designs of these gas masks, and the challenge was the same. You may make a very good mask which will keep out the dust. Essentially that will be some carbon in amorphous form which has small pores. And if you didn't design the pores properly, most of the gas would not even reach the nose. It will be just blocked. And then they came to this concept called percolation of the gas. The pores should be connected to each other in a manner that it forms a continuous network and it's able to reach from one end to the other. At the same time, they should not be so big in size that they don't protect you from whatever their objective is. A very different example, since I emphasize this concept of universality, is propagation of a disease in plants, say in an orchard. So this is a top view of an orchard where these plants are placed at regular intervals. Something placed on regular intervals is called a lattice. These occupy, each of these points is a lattice point. And now imagine at this point a disease has started because the branches of the different trees touch each other. So the disease can easily spread from one to the other and it can follow a certain path. That's a connected path, just like in the gas mask the open spaces were connected. Here the tree branches are connected. This is a big problem because a single tree can end up infecting the entire orchard. It depends on the spacing between the trees and so on. And farmers would like to keep the trees as close as possible because that is important for yield. But placing them too close and not worrying about how often they are connected with each other may result in spread of the disease which may kill all the trees. So what is the optimization in this problem is one example of application of percolation theory. But then we begin with this very nostalgic example, and here Shinzo Hattori has an idea for a rumor. Rumors have spread at all levels. It could be in a school, people start talking something which is not true and then it goes on spreading, but also adults do it. Human beings gossip all the time, and this spend substantial time in this activity called gossip. Sometimes it can be very bad, people can spread fake news. And how does this spread? So let's have a look at this. This character got an idea for a rumor and then had 3 close friends. So conveyed this idea to Ninja Hattori, this is Kenichi, and Shishimaru. Don't worry, Shishimaru is a dog. Let's say it's a human-like dog. So now 3 of them know it. From this onward, each of them had 3 friends. They passed it on. From the first round, 1 became 3. Then each of this is 3 into 3. And then we can go on summing this geometric series. How rumor or fake news spreads. Began with 3 raised to power 0 or 1 person. Then after that 3 raised to power 1. 3 people know it in 20 minutes if that's the time the first character took to tell the others. But 20 more minutes have gone and each of those 3 characters are talking to their next 3 friends. So then 9 people know it, and after say a few hours 3 raised to power 10 or 59,049 people know it. It's a huge number. The problem with this model is very simple. The question we can only ask is how long it will take for the whole town to know it. 59,000 could be a population of a small town. That's a good question to ask, but it's very simple. We can just do this geometric series, geometric progression and get the answer. But then there are thoughtful people who ponder about this, whether I should spread this news or not. Is it true? Is it helping? Have you heard of this 3 filter test? Anybody? Right? So this is, yeah. Yes, so there are these 3 questions given by Socrates, whether the information you are propagating, is it good? That is one. Are you saying something good? Are you saying something useful? And are you saying something which you are absolutely sure that it is true? One of them should be satisfied, need not be all of them. If none of them are satisfied, do not spread that information. But people don't listen to it because there are all kinds of people. So there are thoughtful people where I just imagine these 3 are thoughtful people and the rest are not. The rest are just gossiping and spreading whatever comes to them. In this is the real world situation. So you can't use a geometric series and say 60,000 people will know it. It depends on also whether the news is interesting. Certain kind of gossip will spread very fast, certain gossip will not spread very fast. Then the question is, will the news explode and reach everyone? Now, quote unquote everyone doesn't mean 100% of the population. The emphasis is, will it explode? So it may start from some discussion happening in one locality, then it will go to the town, it will go to the city, the state, the country, and the whole world people would be talking about it. You hear of such things every day. Some of this information is false, but it reaches everywhere. It reaches people in the United States also. Then they start discussing this thing, which never would have happened. This idea shares commonality with how a disease like COVID may spread. Now you can imagine the same kind of a chart, but here what may be spreading is the virus, and certain people maintain more precautions so they don't spread the disease, whereas the others may not. In this picture we have said there are 3 friends for each on average, but the number could be different. It could be 4, 5 or whatever. Yet another example is nuclear chain reaction. A chain reaction happens, but often there could be a mixture of 2 kind of species, one which is undergoing the chain reaction, one which is not participating. Let's say 2 kind of isotopes. And then again you will have this situation of something which tries to spread, something which does not try to spread. And then when does it explode? When will the nuclear bomb explode? Under what conditions? So we look at the answers of these kind of questions maybe more later part of the talk, or the second part of the talk. I'll come to this. Now we'll look at some simpler experiments which will lead us to that. And here I would like to emphasize that great physics experiments do not necessarily need an atom smasher. They don't need to be done in a theory working in 13 dimensions. You can do it with simple things, and this was done with a wire mesh, the kind of wire mesh that you use to keep, say, some rodents out from the air conditioner. That's it, just a very cheap item called wire mesh. And the particular wire mesh which was used by Watson and Leith in 1974, they published their paper in Physical Review. It had 137 sections on one side, 137 on the other side. So it formed a square 137 by 137. Nothing magical about this. Why they chose 137? They could have chosen 138 also. Each of these segments is a piece of metal. It's arranged in this manner. If one applies voltage across this, and there is one electrode put here, let's say a strip of metal, another electrode here, then current will flow through it. And what was the experiment they performed? They brought in a wire cutter. That's all that went into this great paper, a wire mesh and a wire cutter. And they said, we will randomly cut wires, go on cutting wires until the current ceases to flow. You can see some connection with the previous problem. Go on making some characters which don't spread the news until a point that the news explosion stops. So there is a connection with all the previous things I'm showing you. But how to decide which one to cut? Probably one should toss a coin, then say if it is heads, I will cut this. If it's tail, I won't cut this. But doing that would mean you will cut 50% only. Now they would like to say, let's cut 10%, 5%, all kind of percentages, and then see how it evolves. So it's not just tossing a coin. They used a random number generator. I will come to that. Here, this picture depicts what the situation is before and after cutting. This is one of the site where the wires intersect. And if it is intact like this in the original picture, it is depicted with an open circle. Whereas if it has been cut and removed out, the dot has been removed out, it is represented with a black circle, cut and intact. And now with a certain fraction which has been cut and intact, you can see it is filled up with black circles and white circles, and they are randomly distributed. If I really wanted to disrupt the connection, I could have chosen all the black here, but that's not what I'm interested in. In percolation, the distribution of species is quite random, just like in gossip, the distribution of people who spread it and don't spread it is also random. The question they asked is, what fraction of sites are cut when the current stops to flow? And it may appear, should this question even have an answer? Because it's random, I am going to cut, sometimes I may cut along this line a little more, sometimes I may not, and then the question answer will keep on changing. So does this question even have an answer? Is a further question we can ask. But let's go ahead and see what they did. If X is the number of non-blocked sites, that means the sites which were not cut, then they repeated the experiment many times with different mesh, same 137 by 137 mesh, which if you multiply, how many elements are there? A quick answer, just to see if you are on board. 137 by 137, how many such elements are there? Okay, you don't have to be exact, about 19,000 elements are there, 13 squares 169, right? 19,000 elements. It must have taken a very long time to actually perform this real experiment, and they arrived at this precise number 0.59 something dot dot. Now they may repeat it again, they still get it, though the sequence of cutting is different. But when they have removed 41% and 59% are intact, then the current stops to flow. So why is it exact and why do they get it each time? This is a question which we need to answer. So consider for simplicity a 2 cross 2 network. This has only 4 elements which can be removed. They have been labeled as 1, 2, 3, 4. The left side is one electrode, the right side is another electrode. Current is flowing from left to right if a voltage is applied. Let's remove one site. Which side should I remove? Any of them, it doesn't matter. For instance, if I remove one, it's same as removing two because I can rotate it and get the same configuration. So then one site is removed and definitely the current has not stopped, because you can see there are intact connections. The current can go from here to here along this path. It can also change the path and go around here. This connection is also intact. So removing one does not stop the current. Obviously we should try and remove one more and see now if the current stops. Let's remove another site. 4. Well, we removed 3 and now the current has stopped because both of these are removed. There is an air gap. Current can't flow across it. So it suggests that there could be a percolation threshold. Threshold is the number of intact sites when the current stops. What should I say is the percolation threshold in this problem? 0.5, which is different from 0.59. 0.5. Just remember this word because it will be repeated again and again. Percolation threshold. The value of intact sites when the current goes to 0 or when the percolation stops. But that's not the only way. What if I had removed 2 in the second go, not 3 and 4? You can see in this case the current still flows across 3 and 4. So as I said, this question, does it even have an answer? Is there a quantity called percolation threshold? We can't easily say. In 2 situations it gives 0.5, in 1 situation it gives 0.25. The 0.25 is evident because I need to block one more site when the current stops, let's say 4 in the top one, and then only 1/4 of the sites are still intact when the current stops. Working with the definition, you can see Xc is 0.25. So yes, there is no definite answer to the question when the current stops for finite systems, but we can still give a mean value because there are 3 numbers, 0.5, 0.5 and 0.25, with a weighted average because the probability of 0.5 is twice. 2 out of 3 situations, removing 2 is sufficient to stop the current. In 1 out of 3 situation, it requires removing 3. So 0.5 appears twice, half into 2 by 3, and 0.25 appears once. So 1 by 4 is 0.25 into 1 by 3, and the average value is 5 by 12. So an average value for the percolation threshold as 5 by 12 is still defined, though a unique value is not defined. And we can also look at the variance of this quantity, that is how much it deviates from the average. not in this problem, but in general when we set up many problems, you will see that the mean deviation might just be 0. There is an average, sometimes it may go a little higher, sometimes a little lower. So people like to not work with the mean but the square. The variance, which is the value minus the average value, the square. So if you got half as the percolation threshold once, twice actually, so half minus 5 by 12 is the average value, the square of that, and multiplied by the probability 2 by 3, and then quarter was obtained once, minus 5 by 2 the square into 1 by 3. And this has 1 by 72 as the answer. So the root mean square deviation, which is sum over all the delta squares, delta 1 square, delta 2 square and so on, take the under root. It's also a non-zero quantity, under root 2 by 12. It gives a kind of spread in the answers. The answers have this average and this much is the spread in the answers. If the answers are close and close to the mean but they still have a spread, then this will be smaller and smaller. And the picture looks like this. We are looking at percolation, how it forms. Now maybe from the other side, we could start with building bonds, build more and more bonds until you have a situation, enough bonds are there so that the connection has been made. This also reminds me of a game we play in childhood. This I didn't play in my childhood, this I played in my daughter's childhood. That is only a few years back during COVID time. Connect 4. So both of us, she is here, both of us have been playing this during the COVID times. And you can construct this until you have percolation. Sometimes it runs very fast, you know. You make one right connection and then everything gets connected and a huge packet of it is all the points you earn from that. Then this 0.59, is it an average value? Why were they getting 0.59 in every experiment when we just saw that in a 2 cross 2 network you can get a variety of answers and you can only define a mean value. We can calculate through computer programs what is the kind of spread, because they did many experiments, they got 0.59, but maybe they didn't do that many number of experiments. If they had repeated many more, they could have obtained what is the root mean square deviation in that problem, and then for different n values. So they had n of 137 by 137, about 19,000. But they could also do it for 1000 by 1000, 10,000 by 10,000 and so on. And they found this is the very interesting dependence. It's a power law, inverse power law dependence. More the number of sites, then the spread becomes thinner and thinner, and then the root mean square deviation tends to 0 as n tends to infinity. If you have an infinite network of squares, then it will have a unique answer. You may repeat it any number of times, you will always get this. And 137 by 137 is kind of closer towards infinity, it's large number. And so that's the reason they were always getting 0.59. Maybe there will be variations in the next decimal place. The question is why a definite percolation threshold is realized for large n, and this picture gives the answer. Would you like to guess what the answer is based on this picture? Yes. Yeah.
Because they consider B minus as a